Imagine that 2% of your money was catching on fire every month. You probably wouldn't say, oh well, at least the other 98% is still fine. Even tech industry gazillionaires want to preserve as much of their 2% as possible. Personal rockets for space exploration don't come cheap. The same is true in power converter efficiency. Power converters often exceed 98% efficiency, but that means there is still power, and therefore money, being wasted all the time. Recent advancements in silicon carbide transistor technology can help improve performance and reduce power conversion losses. Today's Tech Chat is sponsored by Mouser Electronics, and we are pleased to welcome Pete Losey, the Senior Engineering Manager of Power Devices at UnitedSiC. It's great to have you here with us today, Peter.
Thanks, Dale. Great to be here.
So silicon carbide might be the hottest semiconductor technology in the market these days, and my bad pun is completely intended because it can handle the heat. So Pete, what is our topic for discussion today?
So our topic is about solving the silicon carbide power device design challenges using our new high-performance Gen 4 series 750-volt FETs. And, we really are expanding our portfolio. So back at your pun, you can choose to handle the heat or run cool based on the efficiency and the broad portfolio we have now.
Oh, I'm glad you're embracing my bad puns. So Gen 4, what distinguishes Gen 4 from the previous generations?
So from the previous generation, we've made a significant improvement in the RDS on, or the on resistance per unit area of the silicon carbide FETs. We used to offer a 650 volt Gen 3 portfolio, and now we've moved that up to give another extra 100 volts of margin while cutting the RDS on to specific on resistance.
All right, let's dive in.
Okay, so we're now offering 13 FETs in the series, and the UJ4C represents a side-by-side configuration with the SC representing a stacked die configuration. You know, the sort of flagship product in the series is our new industry lowest RDS on 6 milliohm 750 volt FET, and that's in a standard TO247 package. But the portfolio now really ranges from 6 to 60 milliohms, with new device offerings at 9, 11, 18, 23, 44, and 60 milliohms. For the most of the products, we offer in both a 3-lead TO247 and a 4-lead TO247 package. And with the higher current products, we offer in the 4-lead Kelvin source connected 4-lead package. These devices offer the best-in-class figures of merit in terms of on resistance per unit area. And then because the on resistance per unit area is so low, you can realize an on resistance with a low output capacitance. So they have the benchmark COSS, EOSS times RDS on, and COSS time-related times RDS on. So for a given RDS on, we offer very low QRR, or reverse recovery charge, and turn on and turn off losses. This all kind of comes together to make these parts excellent for hard and soft switching applications. We've sort of maintained our simplicity from the previous generations, where you can drive these with a standard 0 to 12 volt gate drive voltage, which is compatible with existing silicon FET technology. They have a full 5 volt threshold voltage, so this gives good threshold noise immunity. And really, they're flexible, which means you can operate them with the gate drive voltages if you're currently using a silicon carbide MOSFET, a silicon IGBT, or a silicon MOSFET. And with our lowest RDS on part, our 6 milliohm part, we're offering a 5 microsecond short circuit withstand time.
Now, for engineers who may be new to power FETs, can you give a brief explanation of the purpose behind that optional 4th lead in some of these packages?
Sure. So, with the sort of adoption of wide bandgap, what you can do is you can drive quite fast with high DIDTs in a standard TO247 package. So if you think about the RDS on that wide bandgap is offering in a standard footprint package, you're now doing things at speeds that previously couldn't be done. So what that 4th lead does is it's actually a source Kelvin connection. And so the common source inductance of switching off high currents doesn't sort of debias and influence your gate.
Oh, interesting. So the opening slide, you mentioned that these were new devices. What is the current status of the availability?
So with all of these devices, you can get samples now. We're stocking to distributors. So all of these are fully released devices from the 6 milliohm to the 60 milliohm on resistance in the Gen 4 series.
So besides the 4th lead that is shown here, the key product differentiator is the drain source on resistance. So in power applications, this resistance is one of the most critical parameters, isn't it?
That's correct. It probably is the most critical parameter. And we really achieved this superior performance by taking a slightly different approach to our silicon carbide FET. So if you look at the figure on the left, you can see that we actually create our FET in cascode with a low voltage custom silicon MOSFET. And so what our silicon carbide FET has is a very low on resistance, high voltage depletion mode, or normally on silicon carbide JFET, connected in cascode with low voltage silicon MOSFET. And so what you get is you get all the advantage of the on resistance benefit of the silicon carbide JFET with the near ideal gate control of the low voltage silicon MOSFET. And so this allows us to have full 5-volt thresholds with a very low on resistance. And so if you look at sort of the plot in the center of the slide, what you can see is the on resistance versus temperature. And so on the black line on the top, I show the silicon carbide MOSFET on resistance at 650 volts. And then in the blue curve on the bottom, or the darker blue curve below, I'm showing a silicon carbide JFET on resistance. And you can see that at room temperature, it starts much below the silicon carbide MOSFET on resistance. And the reason why is because that on resistance is dominated by still poor inversion mobility, or a very lossy channel portion of the device. As temperature goes up, the bulk mobility of the device drops, and so you get this sort of positive TempCo of on resistance. But if you look at the portion of the silicon carbide MOSFET, the channel resistance, this actually drops with temperature. And so what you'll end up seeing is silicon carbide MOSFET having a flatter TempCo of on resistance, but the silicon carbide cascode FET actually maintains a sizable advantage in specific on resistance over the entire practical temperature range. And a positive temperature coefficient is important because it helps the devices parallel well. And so in the figure on the right, while it is true we have a steeper TempCo, what you can see for 650 volt SiC MOSFETs versus a 750 volt Gen 4 silicon carbide FET from UnitedSiC, we have about a third of the on resistance per unit area at room temperature, and this still maintains a sizable advantage of about 1.x lower at 150C. So all of this comes together with the advantage of having a smaller die size, which gives you lower output capacitance.
And it's kind of counterintuitive that you're stacking two FETs in series, but the sum of those two together is actually a lower drain source resistance than you get with just the one of them. It's a little surprising.
Yeah, and that's right. And it's because really the low voltage silicon MOSFET in here is only a 20 or 30 volt FET. And if you look at the maturity of that silicon MOSFET technology, it's very low specific on resistance. So the net result is the added resistance you put in with the MOSFET, which is near, usually around 1/10 of the total switch resistance, actually doesn't come back to add as much as that silicon MOSFET inversion channel resistance of it.
Yeah, fascinating. So that power lost in the channel is obviously bad for a number of reasons. Certainly you don't want to be wasting power, that's obvious. But in addition, all that channel loss is just heat, which in turn further increases the channel resistance, reduces operating life, and all the other bad things that come along with it.
Yeah. And the other way you can look at it is, as I mentioned, as we go to this slide, is that you can use the specific on resistance advantage to lower your die size and lower your switching loss or your output capacitance or your stored charge in the device. Another way to look at it is for any given footprint, we can always offer a lower total on resistance for the same sort of package size. And so if you look at this slide, we show the industry's lowest RDS on parts for 650 volts and 750 volts, with our new Gen 4 750 volt 6 milliohm FET shown here being less than half of its closest competitor. And these are all in standard discrete packages. So that 6 milliohm part is something that we can put in a small TO247 package. And this, again, has the added advantage of the cascode having better short circuit capability. And so that 6 milliohm device, we're now offering with a 5 microsecond short circuit time, which is shown on the plot above the bar chart. At room temperature, at 400 volt bus, we can survive the 10 microsecond ride through. And then even when you start at the TJ max of the device, you can see that we can offer this 5 microsecond rating.
So what is a typical short circuit withstand time for this class of product?
So in this class of product, what you'll see is in most cases, there's actually not a short circuit rating put on the data sheet. So in this 650 volt class, there's typically not a short circuit rating on the data sheet.
This is pretty amazing, really, because a 2x reduction in a key performance parameter like RDS on for really a mature technology is significant. RDS on is only one of the improved figures of merit that you mentioned earlier back on slide 3. Can you explain to us what those other figures of merit are and why design engineers should care about them?
Yep, sure. So in this slide here, we're showing the three sort of figures of merit that impact the conduction loss or the switching loss in hard switching or the soft switching high frequency capability of the device. So the figure of merits we show here are RDS on time unit area. And as I mentioned, this allows us to get the same RDS on for a smaller area or a lower RDS on for a given area, let's say when you're sort of footprint constrained. In the middle, we're talking about RDS on times EOSS. And you can think of EOSS as a measure of the loss in a hard switching application. And then in the right, we're looking at the figure of RDS on times COSS time related, which is important in soft switching applications where you have very high frequencies and you're looking for low delay times. We also do this again with the smaller die size. It allows us to have lower gate drive losses because we can have a smaller die with lower QG, but also drive from 0 to 12 with a lower gate drive voltage. All of these come with the benefit of having an excellent integral diode, which allows you to actually function reliably even when you come out of resonance in these high frequency circuits.
So that was something that's new to me, this reliable operation out of resonance. What goes wrong here when you have unreliable operation?
So if you kind of look at the one advantage that silicon carbide FETs of all types offer is a very low QRR with low recovery losses when you're hard switching the diode. And so if you come out of soft switching and hard switch that diode, if you look at, let's say, the incumbent devices at 650 volts being silicon superjunction devices, they have a diode that really can't handle that kind of operation.
That's great. Thank you for explaining that to me.
Yep, and this is really shown on this slide here in this radar chart where we're comparing our fourth generation UJ4C 750 18 milliohm K4S against silicon superjunction. And so you can see, again, we offer a higher voltage rating. But then if you look specifically at the diode figures, you can see a QRR of the superjunction devices, which is much, much greater than the recovery charge in our fourth generation FETs. So this is shown here with 1,560 nanocoulombs for the fast diode superjunction FET, with 20,000 nanocoulombs with the lowest RDS on superjunction FET, as compared to only 102 nanocoulombs for the same on resistance part in our technology. They offer a lower RDS on times EOSS figure of merit, being 372 milliohm microjoules against 826 or 911. And again, even then for soft switching, we look at the RDS on times COSS time related figure of merit. And again, we see 108 for the fast diode superjunction and only 8 milliohm nanofarads for our device.
If after all this data, I'm convinced, your Gen 4 750 volt silicon carbide FETs are the way to go for my next power system design, how do I select the right one?
I think the first answer to that is you have to have the right one to select, right? And so we offer this sort of wide portfolio so that you have to, when you're optimizing your system, let's say for thermals or cost or efficiency, you don't have to make really big jumps to the next product offering where you have to end up over designing because of limited selection. And in the sort of next set of slides, we put together some case study to walk you through that decision making to select the right device.
Excellent. So we've been digging into the performance of these Gen 4 silicon carbide FETs. So let's spend some time talking about the applications.
So, UnitedSiC, like many of the silicon carbide component suppliers, are seeing adoption in a number of different applications, both industrial and automotive. And so, again, which application's pulling the part really depends on what part of the broad portfolio we're looking at. As I mentioned, the low RDS on, the low switching loss, the simple gate drive, and even the short circuit performance make these really attractive for traction inverters for 400 and 500 volt bus. So here are 6 milliohm, 9 milliohm, and 11 milliohm products get interest in the simple two-level motor drive inverter. We look to onboard chargers, then we see the front end and the DC-DC converter stages for the main charger and the auxiliary supplies. So here we get interest in the 11 milliohm up to 60 milliohm based on whether it's the auxiliary DC-DC converter or the front end of the OBC. And then finally, growing applications in things like wireless chargers. Here we've got low RDS on products, the 6, 9, 11, and 18. And we've seen interest in the secondary side rectifier, where because we offer a JFET-based technology, we actually see some advantage in having normally off switches in the high side position and a normally on very low on resistance silicon JFET in the low side position. So if you look at the sort of phase lag, it's normally off with the high side normally off device. But then if you have normally on devices in the low side position and you lose gate driver power, then you actually can form a load short for functional safety.
Yeah, the amount of power conversion that's occurring in modern electric vehicles is really astounding. And while efficiency is obviously super important, the reliability has to be a key concern because a product recall in the automotive market is ridiculously expensive.
That's correct. And we have a silicon carbide JFET technology that's based on a bulk technology, which is highly reliable. And it also leverages a very mature low voltage silicon technology, whereas silicon technology has been in the mainstay in automotive power electronics.
Yeah, and then just as we talked about before, the 750 volt gives you that more design margin. That's an advantage for reliability as well.
Correct.
So in this slide, you're showing automotive applications, but you haven't even yet hit on the most obvious one, the plug-in charging of EVs.
That's right. I'm on the off-board charging space, both in automotive and industrial. We offer a lot of advantages. As I said, these devices are great for both hard switched and soft switch applications. So here I'm just showing an example of a phase shift full bridge converter. And then depending on the power level, we really offer between our 6 and 60 milliohm options, a really good choice, no matter what your sort of power level your charger is. And then on the right side here, I'm showing circuit protection. And circuit protection really demands a very low on resistance per unit area, which we feel like we've got the sort of best technology in the class. So here for 6, 9, and 11 milliohms out of our existing portfolio. And again, the key features there are our lowest RDS on per unit area. We offer both normally off and normally on cascode FETs or JFETs, and they have good short circuit and great UIS capability.
Yeah, we tend to think of circuit breakers as being, decades, many, many decades old technology, but there's been a lot of fascinating technology advancements in this area in recent years.
Yeah, and sort of the emergence of solid state circuit breakers really offer very fast braking especially for DC braking, and then added functionality where you can make sort of solid state power controllers with things like inrush, pre-charge limit, and things that are very difficult to do with old sort of mechanical switches.
Exactly. So another major topic in the power industry is power factor correction. So why is that so important, and how did these UnitedSiC FETs benefit?
Yeah, sure. So with the emergence of wide bandgap devices, you can really efficiently go to architecture like totem pole PFC on the front end. And then, as I have already mentioned a few times, the really highly efficient DC-DC converter with the high frequency converter in the DC-DC stage. So again, because you can hard switch the silicon carbide devices, you can go to standard totem pole PFC with very, very high efficiency on the front end. And again, the same sort of themes here: low switching loss for a given RDS on and low output capacitance for that RDS on in the soft switch. Very simple gate drive. So in a lot of cases, we've got customers able to just reuse the existing gate drivers because we offer the 0 to 12 volt gate drive. And our diode has a very low VF, typically between 1.5 volts. So we see a lot of sort of benefit from our 18 to 60 milliohm devices in the sort of IT infrastructure space with the front end totem pole PFC and then the DC-DC converter stage.
Yeah, and applications like this, like a data center, the power conversion efficiency is so important. I mean, you're talking about total energy consumption measured in tens of megawatts. So even fractions of a percent being saved in the conversion process is really significant.
Yeah, and sure. And sort of moving to that totem pole architecture, you're actually getting out, taking sort of one semiconductor drop out of the path rather than a sort of standard diode bridge plus the booster.
Right. And also these data centers tend to move to higher primary system voltages to help reduce the losses. So the 750 volt silicon carbide power FET helps enable those higher voltages.
Yeah, it's great for 400, 390 volt bus. Yep.
Exactly. So can you walk us through the different loss mechanisms for one of these circuits?
Yeah, so I'll just kind of start with a snapshot of slide 13 here and then just move into sort of taking that full sort of stepped portfolio and what that sort of helps you do in terms of optimizing your system design. So we can look at slide 14 where I'm just showing the example of what our portfolio allows a designer to optimize with in an example 3.6 kilowatt on total pole PFC fast leg position. So here I'm starting with the UJ4C 750 18K4S, which is our 18 milliohm device, as the sort of baseline or the starting example. The PFC is running at, the fast leg is running at 65 kilohertz. And as I had mentioned before, it's 230 volt in with a 400 volt DC. And on the left side plot, I'm just sort of plotting the normalized distributor pricing to that 18 milliohm part. And this was represented by the black curve on the figure. And on the right side y-axis, I'm looking at the junction temperature difference designed when compared to that 18 milliohm 750 volt FET in the fast leg positions. So if I look at this, you can see a great semiconductor efficiency with the 18 milliohm FET at 99.4%. If I looked at the breakdown between conduction and switching losses, you're about 45% conduction and about 55% switching loss. So this is a near ideal design for this 3.6 kilowatt, and that's sort of why you get the 99.4% semiconductor efficiency. This all kind of together with a low thermal resistance of the part to give a designed temperature, junction temperature of about 96 degrees C at full load. Now, if you're designing for efficiency and running cool, like we said, this may be the component of choice. But if I go to the next slide and I say, let's take one step up in our new product portfolio to the 23 milliohm FET, now I can see that the conduction and switching losses are almost even more balanced at about 51 to 49%. And it's got an excellent cost performance trade-off. And again, as it's running with a little bit smaller die in there, the junction temperature rise is only a 2 degrees C rise, which is still a very manageable 98 degrees C at full load. This comes with a 20% cost savings in the high frequency leg. Okay, so if we move now up to our 33 milliohm FET, which is the next step up in on resistance in our 750 volt portfolio, we can see that we can achieve about a 40% savings in cost of the high frequency leg with a sort of modest decrease in semiconductor efficiency down to 99.3% and a modest increase in junction temperature up to about 102 degrees C. But now you can see the conduction losses of the device are beginning to dominate the total loss. Here, the conduction loss is about 2/3 of the total loss with the 33 milliohm FET at 65 kilohertz. Moving still up into our portfolio, we can look at the 44 milliohm FET. Again, this is still at 3.6 kilowatts. So here, this is still a manageable 108 degrees C, which is 12 degrees C higher than our baseline case study of the 18 milliohm FET, and a 45% savings in the high frequency leg FET cost. But now the conduction losses are really dominating at 75%. This we think is a good choice where partial load efficiency is important and the converter may spend most of its time at, let's say, at 1.5 kilowatts. At 1.5 kilowatts, this device would offer a 99.4% semiconductor efficiency.
It was a good way to look at it. I mean, someone may look at the top of those and think, well, I mean, 99.1 to 99.4% efficiency, or even from the far right, 98.8. That all seems so high that who cares? But if we flip at it and look at the losses, you know, you're talking about a 2x range in the losses that you're talking about here. So it's significant, really, in the long term.
That's correct. And again, putting more thermal stress on the device means that you have to sort of design more higher performance thermal management systems. So it's really a case of about what we want to do here is offer a wide portfolio, which can offer you the method to optimize your entire system design.
Yeah, that's a great point, Pete, because the cost of the highest performing FET may be a little higher up front in that aspect of it, but the overall, the life of the product, which includes the power management, the heat dissipation, all that kind of stuff, the cooling, and is measured in years or perhaps decades, those efficiency losses and the thermal management are really substantial.
Correct. Yeah, so now looking at the 1.5 kilowatt totem pole PFC case, we can see excellent choices with the 44 milliohm and 60 milliohm devices. You'll notice from the breakdown of the losses, these are roughly balanced in conduction and switching losses, and both options offer a 99.4% semiconductor efficiency. You can see the junction temperature rise when compared to the largest part is almost negligible. So these offer, let's say, the best cost performance trade-off for the lower power designs of 1.5 kilowatts. So really, by putting all of this full portfolio of high-performance Gen 4 FETs together, what we're really saying is that we offer designers new design choices, which allows better system optimization without having to take large leaps or compromise as much between all of their different system requirements.
Yeah, and just here, as you've changed from 3.6 to 1.5 kilowatts, you've shown us the difference, but it's also going to be a function of the architecture that you're looking at.
So as I showed on the previous slides, this was a case study using our FETJet online calculator. But in this slide, we actually show the demonstration of these parts across an actual 3.6 kilowatt totem pole PFC. Here again, the frequency of the fast leg 65 kilohertz, and we're showing the efficiency at Vn at 230 volts with the 390 volt output. And in this plot, you can see the green curve is our baseline device of the 18 milliohm part. The yellow curve being the 23 milliohm, the blue curve being the 33 milliohm, and then the red curve being the 44 milliohm part that we spoke about. And so you can see at full load, the 18 milliohm with its low conduction losses offers a high efficiency. Here we're showing greater than 99%. At half load, you have a great performance cost trade-off with the 23 milliohm and 33 milliohm options, again, being around 99.3%. And then if you're looking at the lower power, as we mentioned before, now the 33 and 44 milliohms look like a very good cost performance option.
It is a great chart. I mean, engineering is always about optimizing that total solution. So performance is one aspect, but cost is another. And so having all these options in your portfolio certainly makes it easier then to find that optimal solution. So now show us what these efficiencies and losses look like for a different converter design.
Okay, so the previous case study showed our new Gen 4 series in the front end totem pole PFC or power factor correction portion of the supply. And now we're looking at, as I mentioned, they're not only great for hard switching, but also soft switching applications. So we're giving an example of a drop-in replacement of existing parts in the DC-DC converter, LLC converter. So here's an example of a drop-in replacement using our new Gen 4 parts in a 3 kilowatt DC-DC LLC converter. You can see the incumbent device being the 31 milliohm 600 volts super junction in the gray, and then our new 33 and 22 milliohm device. And the plot here is showing the efficiency of the converter versus load. And you can see basically by dropping in the parts, we were able to improve the efficiency by almost 0.5% at full load and mid load, and then even more at light load. And again, we're dropping in with a standard 0 to 12 volt gate drive.
Yeah, that certainly makes it easier for people that are looking to make changes to an existing system that they can drop it in. Pete, you've covered a lot of ground for us today. Silicon carbide FET technology, performance metrics, application, circuit performance. So now someone is interested in learning more about UnitedSiC's products and considering them in their next power system design. Where should they go?
Well, they should go to our website at www.unitedsic.com, and there they can find our FETJet calculator. And you can see this is really simple. You can easily evaluate a full range of our products. The new Gen 4 portfolio is already loaded into the FETJet calculator. It supports 26 different unique power topologies. All of the standard topologies are found there in the AC to DC or DC-DC non-isolated or DC-DC isolated converters. And it'll provide results to really all of your fundamental design decisions, as we said, about which component to select, what are the sort of optimal gate drives, how do we recommend sort of starting values to use for things like gate resistors or device snubbers. And you can download a PDF of your design. And again, no registrations required to use the tool.
I wish that tools like these were available when I started as an engineer a long time ago.
It sure beats a sort of wide trial and error.
Yes, it most certainly does. All right, Pete, any last parting words of wisdom for us today?
No, I would just sort of turn everybody to sort of look at our new 750 volt G4 silicon carbide FETs. They are really pushing the sort of performance barriers of what was achievable in standard discrete packages.
Thank you, Pete, for joining us. That is a wrap on our latest edition of Tech Chat, brought to you by Mouser Electronics. We also want to give a shout out to UnitedSiC for loaning us Pete Losi to give us an education on recent advancements in their silicon carbide technology. See you next time on Tech Chats.